In the 1960s, the Tualatin River in northwestern Oregon earned a reputation no community wants. State officials called it Oregon's most polluted river. The water ran so foul that Washington County imposed a building moratorium in 1969, halting development until something could be done about the sewage flowing into the watershed. What happened over the following decades would turn that same river into a model for wastewater treatment, one that utilities across the country now study and attempt to replicate. The Tualatin is not a large river. It winds through the suburbs west of Portland before joining the Willamette, which flows north to meet the Columbia, which empties into the Pacific Ocean roughly 120 miles from where the treated water enters. Every gallon discharged into the Tualatin eventually reaches the sea. That simple geographic fact shaped how Oregon approached the problem of cleaning its water. In 1988, Oregon established one of the nation's first phosphorus limits for a specific watershed. The Tualatin total maximum daily load set a target of 0.1 milligram per liter as a monthly median, among the strictest phosphorus limits anywhere in the country at the time. Treatment plants that had been operating adequately under previous standards suddenly faced an engineering challenge that would take years and hundreds of millions of dollars to solve. The utility responsible for meeting that standard is Clean Water Services, which operates 4 treatment facilities across Washington County. Together, these plants process 66 million gallons of wastewater every day. The 2 largest facilities, Rock Creek and Durham, were forced to develop treatment processes that went far beyond what conventional secondary treatment could achieve. They needed tertiary treatment with advanced nutrient removal, technology that barely existed at municipal scale when the regulations took effect. What emerged from that regulatory pressure was something unexpected. In 2009, the Durham Advanced Wastewater Treatment Facility became the first municipal plant in the United States to install commercial nutrient recovery technology. The system uses a process called PEARL, developed by a company named Ostara, which captures phosphorus and ammonia from the wastewater stream before they can be discharged. 3 years later, Clean Water Services opened a second installation at Rock Creek. That facility became the largest municipal nutrient recovery operation in the world. The technology works by directing side streams from the treatment process into fluidized bed reactors. Inside those reactors, phosphorus and ammonia combine to form crystalline pellets of struvite, a compound that can be sold as slow-release fertilizer. The system captures between 80 and 90% of the phosphorus that would otherwise pass through the plant. It also recovers roughly 20% of the nitrogen. The 2 facilities together now produce more than 780 tons of fertilizer annually, sold under the brand name Crystal Green. The investment paid for itself faster than projected. Rock Creek's $4.475 million installation was expected to reach break even within 6 years through reduced chemical costs and fertilizer revenue. The state supported the project with a $1.12 million energy tax credit, recognizing that nutrient recovery also reduces the energy needed for conventional treatment. Both plants have received national recognition from the Environmental Protection Agency, with Durham specifically cited as the best operated and maintained large advanced treatment facility in the nation. Water quality monitoring tells the rest of the story. Measurements taken between 1992 and 2011 showed that 20 of 27 subbasins in the Tualatin watershed had improving trends for phosphorus, bacteria, or chlorophyll at concentrations. The lower river now meets its phosphorus targets. Summer algae blooms that once choked the waterway have decreased. Perhaps most striking, Clean Water Services now provides roughly 75% of the Tualatin River's flow during dry summer months. The treated effluent has become so clean that releasing it actually improves the river's water quality, rather than degrading it. 60 miles to the east, Portland faced a different but related problem. The city's sewer system dates to the late 1800s, built in an era when engineers combined stormwater and sewage into single pipes. That design worked adequately under normal conditions, but during heavy rains, the combined flow exceeded what treatment plants could handle. The overflow had only one place to go, directly into the Willamette and Columbia rivers, carrying raw sewage along with it. Before Portland addressed the problem, the city averaged 50 combined sewer overflow events every year. Some lasted for days. Each year, roughly 6 billion gallons of untreated sewage mixed with stormwater poured into the rivers that drain to the Pacific. The contamination was predictable, recurring, and for decades accepted as the cost of operating an aging system in a rainy climate. The solution took 20 years to build and cost $1.4 billion. Portland's Big Pipe project constructed massive underground tunnels to capture overflow during storms and hold it until treatment plants could process the volume. The East Side Pipe runs along the Willamette for 6 miles. The West Side Pipe extends nearly 3.5 miles. Together, they can store tens of millions of gallons of combined sewage until the rain stops and the system catches up. The results were immediate and measurable. Combined sewer overflows to the Willamette dropped by 94%. Overflows to the Columbia Slough, which connects to the Columbia River just 18 miles from the Pacific, fell by 99%. The number of overflow events dropped from 50 per year to approximately 4 per rainy season. In January 2025, Portland reached a milestone that would have seemed impossible when the project began: a full calendar year without a single combined sewer overflow, the longest such stretch in the system's history. The Big Pipe was only part of the answer. Portland's Columbia Boulevard Wastewater Treatment Plant, the largest in Oregon, is now undergoing its most extensive upgrade in 50 years. The facility handles an average of 70 million gallons per day, with peak capacity reaching 450 million gallons during storms. It serves approximately 650,000 residents, and its discharge enters the Columbia River, roughly 100 miles from the ocean. The current upgrade is called the Secondary Treatment Expansion Program, known as STEP. The project carries a budget of $515 million and is scheduled for completion in early 2027. In December 2024, construction crews finished 2 new clarifiers, each 150 feet in diameter, the largest components of the expansion. The blower system, that has operated continuously since the 1970s, is being replaced at a cost of $26.3 million. When finished, the plant will be able to treat larger volumes to higher standards, reducing the nutrient load that flows toward the Pacific. The connection between these inland projects and ocean health requires some explanation. Oregon's coast experiences hypoxic conditions, areas of low oxygen, sometimes called dead zones, nearly every summer. But the cause differs from what happens in places like the Gulf of Mexico. Off the Oregon and Washington coasts, the dead zones result primarily from natural oceanic upwelling. Northerly winds push surface water offshore, and cold, oxygen-depleted water rises from the deep to replace it. The summer of 2006 brought the worst recorded event, with oxygen levels dropping to 0.5 milliliters per liter on reefs near Cape Perpetua, causing widespread die-offs of bottom-dwelling marine life. That upwelling process is natural and has occurred for millennia. Wastewater treatment improvements do not directly prevent offshore dead zones. What they do protect are the estuaries, rivers, and near-shore waters where nutrient pollution from human sources accumulates. Harmful algal blooms in Oregon's lakes and estuaries, driven by excess nitrogen and phosphorus from wastewater, agricultural runoff, and septic systems, have generated more than 200 health advisories since 2007 across more than 60 water bodies. Tillamook Bay, Upper Klamath Lake, and sections of the Willamette River all experience nutrient-related water quality problems that improved treatment can address. Coastal treatment plants serve as the final barrier before water enters the marine environment. Unlike Portland's facility, which sits 100 miles from the ocean, coastal plants discharge within miles of the Pacific. Lincoln City's treatment facility, upgraded in phases between 2008 and 2017 to handle approximately 3.3 million gallons per day, releases treated water to Schooner Creek, just 1 to 2 miles from the ocean. The plant switched to ultraviolet disinfection in 2012, eliminating chlorine from its near-ocean discharge. Coos Bay completed a new treatment plant for its Empire facility in 2020, using sequencing batch reactor technology. A second major upgrade at the city's primary plant began in 2023. Both facilities discharge to the Coos Bay estuary, roughly 5 to 10 miles from the open ocean. Astoria's plant releases to the Columbia River at mile 18, just 18 miles from where the river meets the sea. Florence recently upgraded to ultraviolet disinfection and now achieves zero measurable fecal coliform in its treated water before discharge to the Siuslaw River estuary, 5 miles from the Pacific. These facilities have addressed the contaminants they were designed to remove, but a new category of pollution has emerged that conventional treatment cannot handle: PFAS. Often called forever chemicals because they do not break down naturally, pass through wastewater treatment plants essentially unchanged. The compounds enter the system through industrial discharge, household products, and firefighting foam. Then they exit in treated effluent or concentrate in the solid waste left behind. The Oregon Health Authority has identified PFAS in 35 public water systems across the state, with 24 exceeding standards set by the Environmental Protection Agency. Current treatment plants lack the technology to remove these compounds. Options exist, including granular activated carbon, ion exchange systems, and reverse osmosis. But retrofitting existing facilities would cost hundreds of millions of dollars statewide. Oregon is beginning to respond. In April 2025, the Department of Environmental Quality announced plans to add 6 PFAS compounds to the state's list of hazardous substances, the first update to that list in approximately 20 years. Portland's Columbia Boulevard plant has begun sampling to identify where PFAS enters its system. Oregon State University's Clean Water Technology Initiative, funded by a $3.28 million gift in 2018, is researching advanced treatment methods, including PFAS removal through electrodialysis. Federal infrastructure funding is providing $11.5 million annually from 2023 through 2026, specifically for emerging contaminant research and response. Beyond treatment, Oregon utilities have pursued strategies to reduce discharge volumes entirely. More than 120 communities across the state now use recycled water for irrigation, industrial processes, and landscape maintenance. The Metropolitan Wastewater Management Commission, serving Eugene and Springfield, operates the BioCycle Farm, where 600 acres, including roughly 400 acres of poplar trees, have been irrigated with recycled water since the 1980s. The trees absorb nutrients while producing commercially harvested timber. The facility now generates 470,000 cubic feet per day of renewable natural gas from its digesters. Approximately 95% of biosolids generated in Oregon are applied to agricultural land rather than sent to landfills or discharged. Portland's program has operated for 30 years, sending treated solids to farms in eastern Oregon, where the material adds nitrogen, phosphorus, and trace minerals to the soil. Clean Water Services operates a 1.7 megawatt cogeneration system at its Durham facility, powered by biogas from anaerobic digestion. It produces 60% of the plant's electricity and saves $800,000 annually. The work is far from complete. A 2021 assessment identified $7.6 billion in water infrastructure needs across Oregon, with $4.3 billion of that specifically for water quality projects. Much of the state's treatment infrastructure is more than 50 years old. Climate change adds pressure. Projections suggest that roughly 26 Oregon infrastructure sites could face flooding twice annually by 2050, with that number potentially rising to 86 sites by the end of the century. Sea levels along the Oregon coast may rise up to 6 inches within 16 years. Federal funding is helping to close the gap. The bipartisan infrastructure law is directing more than $92 million into Oregon's Clean Water State Revolving Fund between 2022 and 2026, with nearly half available as grants for disadvantaged communities. Individual projects continue to advance. Lake Oswego closed on a $123 million federal loan in 2025 to replace its 1960s-era treatment plant. Klamath Falls is investing between $65 and $100 million in enhanced nutrient removal capacity. What Oregon has built over the past 3 decades represents a fundamental shift in how wastewater is understood. Facilities that once simply treated and discharged now recover energy, manufacture fertilizer, and supply recycled water. The rivers that carry their effluent run cleaner than they have in generations. The ocean that receives those rivers benefits from every upgrade, every captured pound of phosphorus, every gallon kept out of the overflow. The Tualatin, once the most polluted river in the state, now receives water clean enough to improve its quality. That transformation took decades of investment, strict regulations, and engineering solutions that did not exist when the problems were first identified. It also remains incomplete. PFAS moves through the system uncaptured. Infrastructure ages faster than funding allows replacement. Climate change raises the stakes with each passing year. The work continues because the alternative is clear. Every river in Oregon eventually reaches the Pacific. What enters the water upstream arrives at the ocean downstream. The question Oregon has answered, partially and provisionally, is whether communities can interrupt that flow, capturing what should not reach the sea and returning what remains to a condition the ocean can accept. The answer, so far, is yes. But only with constant effort, sustained investment, and the recognition that clean water is not a problem solved once, but a commitment renewed with every gallon treated.